Hi, hello lads. Welcome back. So this is a particularly some might call it a nasty version of an induction, but I actually love these. These are divisibility proof by induction. So in plain English, what we're going to do is we're going to prove that something is divisible by a particular integer using induction. Okay, so the one I've picked, okay, we're going to prove that 2 to the power of 3n minus 1 plus 1 is divisible by 7. Okay? And obviously this is for n is an element of the natural numbers. So for any natural number I put in there, it's going to be divisible by 7. Okay? So let's do our usual step 1. And again, this is the same as all our other ones. Prove it's true for n equals 1. Okay, so is 2 to the power of 3 times 1 minus 1 plus 1 divisible by 7. Well, let's see that. 3 times 1 is 3. 3 take away 1 is 2. So 3 times 1 is 3. Take away 1 is 2. Okay. And let's see if I got that right. Oh, sorry. Plus 3. I was thinking we'd be here all day trying to make that divisible. It's plus 3. That's not close. So let's check, is that right? 3 times 1 is 3. 3 take away 1 is 2. 2 squared is 4. 4 plus 3 is 7. And that is true. 7 is divisible by 7. Okay, step 2. Assume it's true for n equals k. In other words, 2 to the power of 3k minus 1 plus 3 is divisible by 7. Now, I'm not going to keep writing this, and with all divisibility proofs, you don't keep writing is divisible by 7. Let's put it into kind of algebra. Okay, so rather than that, we'll just say 2 to the power of 3k minus 1 plus 3 is equal to 7 times a number. I won't use n, let's use lmn, o, won't use o. Let's use p, 7p. Okay, so 7 times a number. So that would be a multiple of 7. So in other words, whatever that is, it's a multiple of 7. That's the best way of kind of describing it. Okay, let's do our step 3. Step 3, prove it's true for n equal to k plus 1. Okay, so let's put our k plus 1 in here. 2 to the power of 3 k plus 1 minus 1 plus 3. So let's have a look at this one. 2 to the power, let's make this nicer. 2 to the power of 3k plus 3 minus 1 is plus 2. And then we still have our plus 3. So this is our k plus 1. And this is our k. Now, the strategy with divisibilities is slightly different. Usually we would just add this to this to get the new version. Okay? But we can't, because we're not dealing with adding, we're dealing with multiplication and division. Okay? So the trick really is to manipulate this in such a way that you can find it in here. Okay? So that is always the trick with these ones. Now, it's not that it's ever hard. It's always going to be easy to manipulate them. Okay? But it's figuring it out. Okay? So let's have a look at it. Okay? So we have 3 to the power of k plus 3 minus 1. Okay? Which is 3 to the power of k plus 3. Okay, so what we're going to do is we're going to take this original one, if you can see it, okay, and from step 2, I'm going to rearrange it so I have 2 to the power of 3k minus 1 equal to 7p plus 3. Sorry, minus 3. Okay, so all I've done is taken step 2 and rearrange it to get the indice on its own. Okay, and what I'm going to do with this, okay, if you look very carefully, this is our k plus 1 version. Okay, what I'm going to do with this is I'm going to rearrange it. Okay, so I want to be able to find this in this. And you're thinking to yourself, well, I can't find this in this. Okay, I can't. But you can. If you look very carefully, the 3k is already in there. The minus 1 isn't. Okay, however, what I could do is I could rearrange from step 2. Sorry, from step 3. I could turn 2 to the power of 3k plus 2 into 2 to the power of 3k minus 1 plus 3. Okay, so if you look at it very carefully, that and that are the same thing, because I'm just going to separate the plus 2 into a minus 1 and a plus 3. Okay? Now, because of indice rules, I can turn this, okay, I can turn this into 2 to the power of 3k minus 1 times 2 to the power of 3. Can you see that? Because an indice rule says you can if you're multiplying two bases, it's the same as adding their indices. So I'm just decomposing this giant indice into two separate ones with the same base. So really, your step 3, which is this, is actually this, and then I'm just going to tag on a plus 3. Okay? So you're thinking to yourself, right, well, how does that help me? Okay, well, from step 2, I know that this is actually 7p minus 3. Okay, and this is actually a number, it's 8. So that's actually 8 times 7p minus 3 plus 3. Okay, so I'm going to multiply that out. So remember, this has to be divisible by 7. 7 eighths are 56 minus 24 plus 3. Okay, so you can see it. I'm sure some of you can see it. 56p minus 21. And would you believe they're both multiples of 7? So there you go, proving it. So what do we say? If it's true for n equals to k plus 1, it must be true for n equals to k, and if it's true for n equal to 1, must be true for n equal to 2, etc. And that's how you go about proving them all. Okay? So I'm going to show you that again very carefully, because this is a tough one. Once you've done your step 1 and step 2, when you set up your step 3, you rearrange your step 2 so you only have the indice bit on its own, and then you try and find a way of separating your step 3 so that you find the indice in it and substitute in what you've rearranged from step 2. And once you do that, it'll follow down. You will then find it. If you factorize out, you'll find the divisor in there. Okay, so give one of them a go and see how you get on.